In astronomy, axial tilt, also known as obliquity, is the angle between an object's rotational axis and its orbital axis, or, equivalently, the angle between its equatorial plane and orbital plane. It differs from orbital inclination. At an obliquity of 0, the two axes point in the same direction, i.e., the rotational axis is perpendicular to the orbital plane. Over the course of an orbit, the obliquity usually does not change considerably, and the orientation of the axis remains the same relative to the background stars. This causes one pole to be directed more toward the Sun on one side of the orbit, and the other pole on the other side, the cause of the seasons on the Earth. Earth's obliquity oscillates between 22.1 and 24.5 degrees on a 41,000-year cycle. It is currently 23 degrees 26 minutes 13.6 seconds and decreasing. Standards. There are two standard methods of specifying tilt. The International Astronomical Union defines the north pole of a planet as that which lies on Earth's north side of the invariable plane of the solar system. Under this system, Venus is tilted 3 degrees and spins retrograde, opposite that of most of the other planets. The IAU also uses the right-hand rule to define a positive pole for the purpose of determining orientation. Using this convention, Venus is tilted 177 degrees. Earth's orbital plane is known as the ecliptic plane, and Earth's tilt is known to astronomers as the obliquity of the ecliptic, being the angle between the ecliptic and the celestial equator on the celestial sphere. It is denoted by the Greek letter epsilon. Earth currently has an axial tilt of about 23.4 degrees. This value remains approximately the same relative to a stationary orbital plane throughout the cycles of axial precession. However, because the ecliptic moves due to planetary perturbations, the obliquity of the ecliptic is not a fixed quantity. At present, it is decreasing at a rate of about 47 inches per century. History. Earth's obliquity may have been reasonably accurately measured as early as 1100 BC in India and China. The ancient Greeks had good measurements of the obliquity since about 350 BC, when Pytheas of Marseille measured the shadow of a gnomon at the summer solstice. About 830 AD, the Caliph al-Ma'mun of Baghdad directed his astronomers to measure the obliquity, and the result was used in the Arab world for many years. It was widely believed, during the Middle Ages, that both precession and Earth's obliquity oscillated around a mean value, with a period of 672 years, an idea known as trepidation of the equinoxes. Perhaps the first to realize this was incorrect was Ibn al-Shatir in the 14th century, and the first to realize that the obliquity is decreasing at a relatively constant rate was Fracastoro in 1538. The first accurate, modern, Western observations of the obliquity were probably those of Tycho Brahe from Denmark, about 1584, although observations by several others, including Al-Ma'mun, Al-Tusi, Purbach, Regiomontanus, and Walther, could have provided similar information. Seasons. Earth's axis remains tilted in the same direction with reference to the background stars throughout a year. This means that one pole will be directed away from the Sun at one side of the orbit, and half an orbit later this pole will be directed towards the Sun. This is the cause of Earth's seasons. Summer occurs in the northern hemisphere when the North Pole is directed toward the Sun. Variations in Earth's axial tilt can influence the seasons and is likely a factor in long-term climate change. Oscillation. Short-term. The exact angular value of the obliquity is found by observation of the motions of Earth and planets over many years. Astronomers produce new fundamental ephemerides as the accuracy of observation improves and as the understanding of the dynamics increases, and from these ephemerides ephemerides. Various astronomical values, including the obliquity, are derived. Annual almanacs are published listing the derived values and methods of use. Until 1983, the astronomical almanac's angular value of the obliquity for any date was calculated based on the work of Newcomb, who analyzed positions of the planets until about 1895. Epsilon equals 23 degrees 27 minutes 8.26 seconds minus 46.845 t minus 0.0059 t2 plus 6 quintillion 997 quadrillion 181 trillion spade suit 0.00181 t3, where epsilon is the obliquity and t is tropical centuries from B 1900.0 to the date in question. From 1984, the Jet Propulsion Laboratories, a series of computer-generated ephemerides, took over as the fundamental ephemeris of the astronomical almanac. Obliquity based on DE 200, which analyzed observations from 1911 to 1979, was calculated. Epsilon equals 23 degrees 26 minutes 21.45 seconds minus 46.815 t minus 0.0006 t2 plus 6 quintillion 997 quadrillion 181 trillion spade suit 0.00181 t3, where hereafter t is Julian centuries from J 2000.0. JPL's fundamental ephemerides have been continually updated. For instance, the Astronomical Almanac for 2010 specifies epsilon equals 23 degrees 26 minutes 21.406 seconds minus 7 quintillion 1 quadrillion 468 trillion 367 billion 689 million 999,999 spade suit 46.83769 t minus 6 quintillion 996 quadrillion 183 trillion 100 billion spade suit 0.001831 t2 plus 6 quintillion 997 quadrillion 200 trillion 339 billion 999 million 999,999 spade suit 0.00200340 t3 minus 5.76 times 10 minus 7 t4 minus 4.34 times 10 minus 8 t5. These expressions for the obliquity are intended for high precision over a relatively short time span, perhaps plus or minus several centuries. J. Lasker computed an expression to order T10 good to 0.02 over 1,000 years and several arcseconds over 10,000 years. Epsilon equals 23 degrees 26 minutes 21.448 seconds minus 4,680.93 t minus 1.55 t2 plus 1,999.25 t3 minus 51.38 t4 minus 249.67 t5 minus 39.05 t6 plus 7.12 t7 plus 27.87 t8 plus 5.79 t9 plus 2.45 t10, where here t is multiples of 10,000 Julian years from J 2000.0. These expressions are for the so-called mean obliquity, that is, the obliquity free from short-term variations. Periodic motions of the Moon and of Earth in its orbit cause much smaller short-period oscillations of the rotation axis of Earth, known as nutation, which add a periodic component to Earth's obliquity. The true or instantaneous obliquity includes this nutation. Long-term using numerical methods to simulate solar system behavior, long-term changes in Earth's orbit, and hence its obliquity, have been investigated over a period of several million years. For the past 5 million years, Earth's obliquity has varied between 22 degrees 2 minutes 33 seconds and 24 degrees 30 minutes 16 seconds, with a mean period of 41,040 years. This cycle is a combination of precession and the largest term in the motion of the ecliptic. For the next 1 million year, the cycle will carry the obliquity between 22 degrees 13 minutes 44 seconds and 24 degrees 20 minutes 50 seconds. The Moon has a stabilizing effect on Earth's obliquity. Frequency map analysis conducted in 1993 suggested that, in the absence of the Moon, the obliquity can change rapidly due to orbital resonances and chaotic behavior of the solar system, reaching as high as 90 degrees in as little as a few million years. However, more recent numerical simulations made in 2011 indicated that even in the absence of the Moon, Earth's obliquity might not be quite so unstable, varying only by about 20 to 25 degrees. The Moon's stabilizing effect will continue for less than 2 billion years. If the Moon continues to recede from Earth due to tidal acceleration, resonances may occur which will cause large oscillations of the obliquity. Solar system bodies. All 4 of the innermost rocky planets of the Solar System may have had large variations of their obliquity in the past. Like Earth, all of the rocky planets have a small precessional rotation of the spin axis. This rate varies due to, among other things, tidal dissipation and core mantle interaction. When each planet reaches certain values of precession, orbital resonances may cause very large chaotic changes in obliquity. Mercury and Venus have most likely been stabilized by the tidal dissipation of the Sun. Earth was stabilized by the Moon, as above, but before its capture, Earth, too, could have passed through times of instability. Mars's obliquity is currently in a chaotic state. It varies as much as 0 degrees to 60 degrees over some millions of years, depending on perturbations of the planets. The obliquities of the outer planets are considered relatively stable. Some authors dispute that Mars's obliquity is chaotic, and show that tidal dissipation and viscous core mantle coupling are adequate for it to have reached a fully damped state, similar to Mercury and Venus. Extrasolar planets. The stellar obliquity (i.e., the axial tilt of a star with respect to the orbital plane of one of its planets) has been determined for only a few systems, but for 49 stars as of today. The sky-projected spin-orbit misalignment lambda has been observed, which serves as a lower limit to psi. Most of these measurements rely on the Rossiter-McLaughlin effect. So far, it has not been possible to constrain the obliquity of an extrasolar planet, but the rotational flattening of the planet and the entourage of moons and/or rings, which are traceable with high-precision photometry, e.g., by the space-based Kepler spacecraft, could provide access to Psi-P in the near future. Astrophysicists have applied tidal theories to predict the obliquity of extrasolar planets. It has been shown that the obliquities of exoplanets in the habitable zone around low-mass stars tend to be eroded in less than 109 years, which means that they would not have seasons as Earth has.